Hello, in this video, we are going to take a look at one more example of using these power series to find other power series for different functions. So first, we're going to start off with this 1 over 1 minus x. Say we want to find the power series for 1 over 1 plus x squared. Well, this is the composition idea. I want to make 1 over 1 plus x squared look like 1 over 1 minus x. So that is 1 over 1 minus negative x squared. Which equals the series k equals 0 to infinity of negative x squared to the k. So plugging that negative x squared into the position for x. And now just rewriting our series to distribute that k, we'd have negative 1 to the k x to the 2k, which converges for the absolute value of the thing I put into that x position, negative x squared less than 1. Solving out this inequality, the negative gets dropped because it's an absolute value. So we have the absolute value of x squared is less than 1. And taking the square root of everything, the absolute value of x is less than 1. Meaning, our final conclusion for this is that 1 over 1 plus x squared is equal to the series k equals 0 to infinity of negative 1 to the k, x to the 2k, for the absolute value of x being less than 1. The interval of convergence, if we wanted to write it out, is negative 1 to 1. That's what absolute value of x being less than 1 means. Now, we want to use that power series to find a representation centered at 0 for arctangent. So we have the function of 1 over 1 plus x squared, which has the power series of k equals 0 to infinity, negative 1 to the k, x to the 2k, with an interval of convergence of negative 1 to 1. How can I get arctangent from 1 over 1 plus x squared? Well, we know the integral of 1 over 1 plus x squared is arctangent. So if I integrate g of x, I will get arctangent. So the integral of g of x dx is equal to arctangent x. And so if I need the power series of this, if I need the power series of arctangent, then I want to integrate the power series of 1 over 1 plus x squared. Using the power rule that the integral of x to the k is equal to x to the k plus 1 over k plus 1 plus c, taking the integral, we will have k equals 0 to infinity. The negative 1 to the k stays the same because it doesn't have any x. But the x to the 2k, I'll apply the power rule to get 2k plus 1 all over 2k plus 1. So there is my power series. This plus c, because we still have an indefinite. So the integral of g of x dx is equal to arctangent of x which is the series k equals 0 to infinity of -1 to the k x to the 2k plus 1 all over 2k plus 1 plus c. When we integrate, there's two things we need to do. We need to find the interval of convergence, which is going to be -1 to 1 somehow. We need to check those endpoints. The other thing is we need to figure out what c is. Well, to find c, we'll do that first. What is c? We're centered at 0. So let's see what happens when I plug 0 into arctan and into the power series. Then arctan of 0 is equal to the series k equals 0 to infinity of -1 to the k, 0 to the 2k plus 1 over 2k plus 1 plus c. Arctangent of 0 is 0. And the series, we have 0 to the 2k plus 1 over stuff and multiplied by stuff. Ultimately, that series is 0 plus 0 plus 0 plus 0. The series is all 0 plus c. C equals 0. So in this case, once again, c is 0. So we actually have the power series already. C could be coming out to be any other number, but in our two examples, we've had it come out to be 0. And then the last thing, now that we have what c is, we do also want to check those endpoints. If x equals 1, we will have the series k equals 0 to infinity of -1 to the k, 1 to the 2k plus 1 over 2k plus 1. 1 to the 2k plus 1 is just a 1, so that's not doing anything. But we have -1 to the k over 2k plus 1. We can use, and I'll leave you to practice it, we can use the alternating series test to see that this will converge by the alternating series test. So 1 is now part of our interval of convergence. If x equals -1, we'd have the series k equals 0 to infinity, -1 to the k, -1 to the 2k plus 1, all over 2k plus 1. Simplifying this out, -1 to the 2k plus 1 is also -1 to the 2k times -1. And -1 to the 2k is -1 to the k squared. And anything squared becomes positive, meaning that piece is just 1. Making this series, actually, the series k equals 0 to infinity of -1 to the k plus 1. We have -1 to the k times -1. So that's -1 to the k plus 1 over 2k plus 1. Once again, this converges by the alternating series test. So we can find that these converge both at x equals 1 and at x equals -1, making our interval of convergence, it went from -1 to 1 without including -1 and 1. And now we do include -1 and 1. So for x in -1 to 1. And then the final thing we can do, it says use this power series now. So the power series of arctan of x being equal to the series k equals 0 to infinity of -1 to the k, x to the 2k plus 1 over 2k plus 1 for x in -1 to 1. Use this power series to find the power series for f of x equals arctangent for x squared. X being in -1 to 1 can also be written as -1 is less than or equal to x is less than or equal to 1. And so to find arctan of 4x squared, we're going to take that 4x squared and plug it into x in all those positions. So take that 4x squared and compose it in. We get arctan of 4x squared is equal to the series k equals 0 to infinity of -1 to the k, x to the 2k plus 1. But x is now 4x squared, the 2k plus 1, all over 2k plus 1. Switch these out to have all the same color. Arctan of 4x squared is equal to that series. For -1 is less than or equal to the 4x squared is less than or equal to 1. So the only thing that's changed between the red line and the blue line is that all the gray x's have become 4x squares. We essentially have this answered, but what we really need to do to fully answer it is to simplify everything. So we have arctan of 4x squared is equal to the series k equals 0 to infinity of -1 to the k, 4 to the 2k plus 1, x to the 4k plus 2 by multiplying 2 by 2k plus 1, all over 2k plus 1 for dividing everything by 4. We'd have -1 over 4 being less than or equal to x squared, which is less than or equal to 1/4. And then taking the square root of 1/4 is 1/2. Might be saying, but wait, we can't take the square root of -1/4. The issue here is that this line is actually coming from an absolute value of x is less than or equal to 1, meaning the absolute value of 4x squared is less than or equal to 1, or the absolute value of x squared is less than or equal to 1/4. And now by exponent rules, I can take the square root and have the absolute value of x is less than or equal to 1/2. So technically, couldn't take the square root of -1/4, but because of the line that we're looking at the absolute value, we can. But we have now answered that question of the arctangent of 4x squared is also the power series, -1 to k of 4 to the 2k plus 1 x to the 4k plus 2 over 2k plus 1 for any x's that are between negative 1/2 and 1/2. So if I plug in, say 0, that is the center, and we already know arctan of 0 is 0. But if I plug in something like 1/4, then I would know that arctangent of 1/4 is equal to the series negative 1 to the k, 4 to the 2k plus 1, 1/4 to the 4k plus 2 over 2k plus 1. So we have a lot of things now that we can do with these power series. In particular, we can combine and integrate and differentiate power series. And we have done all of those in this sample problem.